So, projectiles. These are objects that are thrown or launched in the air and are subject to gravity. And we'll mention gravity again before it's over with. It is a curved path, and it follows when thrown, launched, or otherwise projected near the surface of the earth, and it takes on a parabolic trajectory. And we're going to ignore air resistance in anything that we do. Parabolic trajectory. Anybody have an idea? So this is showing you, and this picture is fairly important, so make sure you make a note of it. You need to go back and look at it if you don't completely understand what we're talking about now. If we look at free fall has an initial horizontal velocity. The ball in red, what are you doing there?
Dropping it.
It's just being dropped, okay? There is no type of parabolic motion to it. There's no angle associated with it. We're mainly going to work with stuff that's at an angle. But if it is dropped right there, and you had to describe horizontal and vertical velocity, what would the horizontal velocity be? Zero. Because there is no horizontal motion to that if it's being dropped straight down. So all the motion there is going to be in the vertical. If you look at the yellow ball, though, it does have an initial horizontal velocity. Okay? And if we look at that, and I want to draw something on here. When it talks about initial horizontal velocity, that's the v sub x right there. You're going to see it a lot. But that does have an initial horizontal velocity. So initially, there is nothing in the y direction velocity-wise. So nothing that is vertical. All velocity is in the x. It also points out that if you look at the red balls and they've got all these little lines out here to the side, what does that mean?
Time, seconds.
Okay. What about red ball in relation to the yellow ball? It's the same. Okay. Both of them are going to fall with the same velocity. They're supposed to hit the ground the same. This is assuming there's no air resistance, no kind of friction to slow it down. They'd be dropped in a vacuum. Okay?
Projectile motion describes the motion of objects that are in free fall but have an initial horizontal velocity. Both balls are released at the same time and fall with the same downward acceleration. The initial horizontal velocity of the yellow ball does not affect its vertical displacement. As the ball leaves the pitcher's hand, it has a constant horizontal velocity. The force of gravity acts on the ball and accelerates it downward, causing its vertical velocity to increase. The two motions cause the ball to move in a curved path, known as a parabola. Air resistance changes the path of a projectile. When traveling through Earth's atmosphere, the projectile's path is not a parabola.
Looking at that, again, one of the things they mentioned was whenever you have to talk about gravity, do you remember what we used as our velocity to represent gravity? Okay, well, the acceleration, and we're going to get to the acceleration. So acceleration is 9.8 meters per second squared. And we will end up using that. Getting into what they call kinematic equations. What do you think the word kinematic comes from?
Motion.
Kinetics, which is something that is in motion. We are going to talk about that second bullet. It's talking about resolving vectors into components. Again, if we have this parabolic motion here, then you can have something in the x direction, and you will have motion in the y direction. So we will be looking at this as far as, can we get this as a 90-degree angle and make some mention of whatever it is we're going to do. So there's acceleration. Again, if you have not memorized that number for acceleration, 9.81 meters per second squared. That needs to be stored away in your brain somewhere. Why do they have it as a negative?
Because gravity is falling.
Gravity is considered a downward motion, and down is considered a negative direction. So negative 9.81. Well, it's acceleration due to gravity. So if this is the way you're going to see us write it, they say a sub y. We're going to call it a sub g, and that's acceleration due to gravity. And in some books, they'll call it just lowercase g, which is still acceleration due to gravity. So let's look at this first one. Projectiles that are launched horizontally. It says the initial vertical velocity is 0 and the initial horizontal velocity is your initial velocity. And then you've got those that are launched at an angle, and we're going to look at both. And it's going to be important whenever you read your different word problems you've got is this something that's falling from rest? Is this something that is being launched just horizontally? Or is this being something that is being launched at an angle? Because that will help you determine which set of equations that you go to look at. So again, if I'm looking at the first one, it's just like the red and yellow ball that we saw. You know, if this is the edge of the table and that's my ball, what is going on with it? Okay? So all of your velocity for a situation like that is in the vertical direction. Every bit of your velocity is in the vertical direction initially, when it starts. And in the bottom one, if you launch it at an angle, what is it that they're doing? Say you've got a ball right here and it's being launched at an angle. They have an angle that's mentioned. But also, look, they break it into components. They have a component in the x and a component in the y direction. So, in the first two sections, when we kept dealing with components of our resultant vector, this vi that they have here, that initial velocity, it has components in the x and y direction. So expect for like things like sine and cosine to start to play a role in these type of equations. So we're going to look at all of the equations before we get to the example. Starting off with, this is going to be vertical motion of a projectile that falls from rest. So, vertical motion, and it is falling from rest. Okay, that's V sub YF. What do you think the Y means? Vertical motion. What do you think the F means? Final. So at the final velocity in the Y direction. The A sub Y. It's going to be acceleration in the Y direction, which is typically gravity. Typically your gravity. So 9.81.
Does that say very minus?
What's that again?
What is the very top say?
That's vertical motion, and it's talking about when you fall from rest. So the falling from rest is the key to this first set of equations that we're going to do. So again, v, and then that is y and f again, but this entire thing is squared this time. Okay, the little subscripts are just there for identification, but that velocity is squared, and then it's 2 times ay delta y. What do you think delta y is? Change in your vertical position. And remember, if it's falling from rest, your change in your vertical position, would that end up being a positive or negative number? Negative, because it initially starts off at a high spot, falls down to something lower. So when you look at that, you're going to have a larger number initially and a smaller number as your final. So you'll end up with a negative number. So if you have a negative delta y and you have a negative acceleration, what happens? You end up with a positive velocity. So the negatives will play a role within this. And the third one we're going to look at is delta y, 1/2 a sub y delta t squared. So that one involves time.
Is the AY the acceleration moving down? So will that be the
Acceleration in the y direction, and the majority of the time that is acceleration due to gravity. Now, next set of equations. That top one was for vertical motion. What about horizontal motion of a projectile? Horizontal motion of a projectile. And this top one, that was the ball that was basically just dropping straight down. Okay? That's what you had right here. Ball dropping straight down. In this one, what is this actually going to represent? Horizontal motion of a projectile. Only horizontal motion. Do you remember the yellow ball?
Yeah.
Okay? This is the kind of motion we're talking about in this set of equations that we're going to give. So the picture we've already talked about, this is what we're looking at. Velocity in the x direction is your initial velocity in the x direction, which is a constant value. Typically, it is given in most scenarios. Occasionally, you might have to solve for it, but the majority of the time, it's going to be given. V sub x or V sub xi, that's x or slash your initial velocity. Remember how we said that your initial velocity in a scenario like this is all in the x direction? That's what it's talking about. And what is delta x? Change in horizontal position. So if I look at my example over here, from the edge of the table to where the ball meets the ground, that would be my delta x. And this is V sub x delta t. What does that last equation remind you of? Velocity equals distance over time. And they've just rearranged it. Velocity is distance over time.
What does that first one say?
In the orange, V sub x equals V sub x I.
Comma?
Yeah, it's a comma. Anytime they put multiple subscripts, they'll put a comma between each subscript. Equals a constant. So, now, those are the equations for if it's launched horizontally or launched at an angle. Now, we're going to get to an example problem with this. I think we'll do an example problem with one of these first. Before we get to this sample problem, we need to talk about another set of equations. What?
What?
Yes, there is another set. Here we go. These are what we've not talked about yet. We haven't talked about anything with an angle. So projectiles launched at an angle. I'm sure we'll get to it. So projectiles launched at an angle. We've got 5 here. Starting off, you've got real simple stuff. So v sub xi is the same as vi cosine theta. And you've got v sub yi is equal to vi sine theta. And again, this was the last drawing we looked at where it had the coordinates, or not coordinates, but the components for v sub I in the x and y direction. So we are projecting or launching at an angle. We've got this, and we are launching at an angle. So, earlier when we were not launching at an angle, we didn't have to worry about the theta part of this, but still Vx is going to be a constant. Delta x, which is our horizontal motion. Same equations from what we just looked at. Our only differences in this one is we have added in cosine theta. It's the only difference. Are y'all going to have to memorize these equations? No.
Oh.
No.
That was a surprise.
Yeah. Hey, I've got something to say about that. It was an email I got today.
What?
I'll tell you when we're done.
You got an angry email?
No, it was a good one.
Oh.
I mean, good for me. Maybe not for y'all, but it's good for me.
Wait, what
We'll talk about it. It's talking about memorization and what all you had to know in college and all that other good stuff. Yes.
Why?
No. No. And I'm trying to get them to come talk one day to all my classes. It might be during their fall break.
They can talk as a couple. Oh my gosh. Talking about getting married.
Well, and I asked Sarah Winfield to come too.
Sarah Winfield?
Mm-hmm.
The email?
No. No, it was when I saw him. Okay, so here are, you've got the 2 up there, which just adding angle, and then you've got these 5 equations here, and again, even that third one is just adding an angle. Do these equations look like anything special similar to what you might have seen before? Maybe. Maybe from, I'm thinking Chapter 2, Section 2. When we did Chapter 2, Section 2, and we talked about acceleration, it is these equations from Chapter 2, okay? It's the same equations from Chapter 2. We're just adding in our angle where it is appropriate. Okay? That delta y, we're going to get into a lot of what if this and what if that, and because there's lots of crazy scenarios you can get into, and we'll get into those. But on that delta y part, this bottom part right here basically is like your upward component, and then this part right here is your downward component. Because how would I know that one's really the upward component and one's the downward component? What does the second one have that the first one doesn't have? What I just underlined. Acceleration. So acceleration is going to be something in a downward direction that it's going to affect. You ready for the next sample problem?
Let's freaking do it.
So, famous question here. We will draw this out. A zookeeper finds an escaped monkey hanging from a light pole. Aiming her trink gun at the monkey, she kneels 10 meters from the light pole, which is 5 meters high. Tip of her gun is a meter above the ground. At the same moment, the monkey drops a banana, and the zookeeper shoots. If it travels 50 meters per second, will the dart hit the monkey, the banana, or neither one? So, again, there's tons of information in this. What would Miss Hopper do first?
Draw it out.
I would draw it out. So you have this on your PowerPoint. Just leave your PowerPoint up because I'm fixing to go draw this out.
I can tell you what she's
Don't spoil it.
Shh. No, don't spoil it for everybody else.
Well, insert it
That monkey deserves to be free if it's
Looking at this. So you've got a light pole. We're going to draw our light pole over here. Yep. It's shining bright. And it says you've got a monkey hanging from a light pole. Oh, Lord, my monkey.
make my life.
Do you like a monkey in?
Yeah. So there's the light. Oh,
Wait,
no.
what is that supposed to be? Fire. Looks more like a matchstick.
Yeah.
Like a mushroom.
Mine's like a old.
Here's my monkey.
Boo.
You're a drink up with like an AR-15.
It's hard with this stylus. I can't. There's no details to this.
I don't have
But you need a clip.
It's an egg.
Okay.
Run around and drink.
Alright, yeah, I'm definitely doing my own spin on mine.
She kneels 10 meters from the light pole. So you've got a person here. Again, I'm going to show her standing, but she is 10 meters from the light pole.
She's wearing a blindfold.
Okay. So that delta X is going to be 10 meters. That's in the horizontal direction. The light pole is, or the monkey is 5 meters high. So 5 meters. That's what we've got right here. Yeah. The tip of her gun is a meter above the ground. So here's her gun.
Also, she is an Uzi.
Yeah.
She has a Uzi.
Mine is like a
There's her gun.
sword.
That is.
That is a triangle, not a gun.
Hey,
She's throwing.
stop. Just stop. Stop. I don't want to get all y'all's background chatter in on this. And the monkey drops a banana. So we've got a banana. The zookeeper shoots. If the dart travels at 50 meters per second, will the dart hit the monkey, the banana, or neither one? So here's what is being shot. So what's going to happen with it? Where is it going to go? And that is going 50 meters per second. How should we label the 50 meters per second?
X acceleration.
Or is it?
Well, it's at an angle. What do you think? VI, 50 meters per second. So VI, 50 meters per second. Delta Y from the monkey to where her gun is. What is delta Y?
4 meters.
Okay, delta Y right now from the monkey to her is 4 meters. And then we've still got the delta X. So is that all of our given information? Say yes.
Yeah.
Okay. I mean, we need to find, well, delta Y is 4 meters, but what about the monkey or the banana? So Y for the banana, where is it at? And then the Y for her dart. Where is the dart actually going to be at, height-wise? So we're talking about the height of the banana as it's falling, and then the height of the dart after it is shot. The angle. This angle that is right here, we're going to try to find it. How are you going to find angle? Do you want to receipt? Okay. Which formula?
Jason, what was it? It'd be tan.
It's going to have to be tangent. Yeah.
Tangent, theta.
Because we have the y and we have the x, right?
Yeah.
Okay. So let's we're going to do tangent theta. Maybe. And tangent theta is change in y over change in x. What are we going to put in for y? The 4. And what are we putting in for x? 10. So you got to solve for theta here. So that's going to end up, you're taking the inverse of 4 divided by 10. For time, because the bell is ringing soon, that's 21.8 degrees. So we have that as 21.8 degrees. No. Okay, so class is over with this, and the rest of this is solved on your PowerPoint. So I'm just going to go back to the PowerPoint, let you see how they solve the rest of this, which is essentially what I would have done. And we'll be using equations that were given to you for what happens if you're at an angle versus not an angle, because we are going to be dealing with some free fall too. So let's go back to the PowerPoint. So this is their drawing they did. I think mine looks just a shade better. And this is them solving for angle, which is the same thing that we did. So now we finally have the angle at which she is shooting her dart. And the next step that they tried to do was they were solving for delta t. Time is used in several of these equations. So you know that the banana is falling. It's going to fall for a certain amount of time until the dart reaches that distance. And you know how long is her dart actually in the air. So time is a very important part of us trying to move forward to the next step. So this is the equation they used to solve for time. And like this one states, how far did each object fall during that time? So they did delta y for the banana. And remember, the banana is falling straight down. So if the banana is falling straight down, velocity initial is equal to 0, because initially it is just dropped. So it has, at rest, it had no velocity. So that is why we are able to use this equation here. And then it shows the dart. The dart did have an initial velocity, so we had to go with an equation that took into account the angle of the dart, how long was the dart in the air, and then also acceleration due to gravity. So you do have delta y, which is vertical for the banana and vertical for the dart. And to figure out what the dart is going to hit, you got to find the final distance of the banana. So they took the 5 meters that you had, which was the distance that the monkey was above the ground, and they subtracted off how far it fell. So there's your 4.77 meters. And then they did the same thing for the dart. And you can tell by these results here, again, the dart started at 1 meter above the ground, and it went an additional 3.76 meters. And based on the results here, it looks like the dart is going to hit the banana instead of the monkey. So, looks like she needs to work on her aim just a little bit more.